This is Related Rates Problem 3. You shouldn't be working on this problem unless you have seen all 3 other videos, Introduction to Related Rates and Problems 1 and 2. This is a hard problem. But no, the problem didn't make me cough. Okay, this is more realistic. We have an inverted water tank. It's shaped like an inverted cone, and you can think of it as an ice cream cone. But geometrically, it's a right circular cone. It has an opening with a 2-meter radius and a 4-meter height. And the height is always perpendicular to the radius. And what's happening here is it's being filled at a rate of 2 cubic meters per minute. And sometimes it's a little difficult to think about what derivative you're given, but the cubic is a definite clue. Cubic usually means volume. And if you think about it, water isn't two-dimensional. Water has volume, so the water is pouring in at a rate of 2 cubic meters per minute, and that's the derivative you're given. And you're asked to find the rate at which the water level is rising. So it's important to realize that you have this empty inverted cone, and you have this blue cone of water that's getting higher as the large tank is being filled. And you're being asked for dH dt. How fast is the height of the actual water in the cone rising? So you're given dV dt, 2 cubic meters per minute, and you have to find dH dt. And the when is precisely when this height is 3 meters deep. Okay, so this is a little more complicated, but now you have the input, and now we have to take the derivative. We have to find our equation and take the derivative. And it's a little more complicated because, as before, we need an equation relating the variable whose derivative we have with the variable whose derivative we want to find, v and h. But the volume of a cone is not just a function of the height of the cone. It's 1/3 pi r squared h. It's a function of the radius of the cone and the height. So we can sense there's going to be a complication here. We can take the derivative, even though it's a function of 2 variables, because we are taking the derivative with respect to time. We're using our implicit differentiation techniques. But we're going to have to deal with the product rule here, because we have r squared times h. These are both functions, and we have to take the derivative using the product rule. So we're going to go forward and take the derivative, and we're going to think about how we might deal with the fact that we're going to have a dr dt in the mix also. And we don't know what dr dt is. Okay, we start out with volume is 1/3 pi r squared h. One technique in using the product rule is to pull out the coefficient. So that's what I did here. I pulled out the 1/3 pi, because that's just a number. And in here we use the product rule on the derivative of r squared h. So this is r squared times the derivative of h with respect to time, dH dt. And then this is h times the derivative of r squared with respect to time. So here we have chain rule. The derivative of r squared, a function squared, 2 times the function, 2 times r, dr dt. And now we can put the 1/3 pi back. We conquered the product rule, and we can get an expression for dV dt. So 1/3 pi r squared dH dt plus 2/3. 2 times a third is 2/3 pi. Rearranging the order here a little bit. 2/3 pi r h dr dt, but you should see it's the same thing. The 2 ended up here, and the r just ended up before the h. So now we did a substitution. We were given dV dt was 2 cubic meters per minute. So that's 1/3 pi r squared dH dt. We don't know anything here. We have to find this, and we don't know what r is. Plus 2/3 pi r h dr dt. We do know that h is 3 meters. That's the instant when we want to find dH dt. So that's going to be substituted in here. So now I'm subtracting this term with the substitution from both sides of the equal sign. So 2 meters cubed per minute minus 2/3 pi r times 3 meters. The height has the substitution dr dt equals 1/3 pi r squared dh dt. We're solving for dh dt even though we don't have all the substitutions we need. So we divide both sides by 1/3 pi r squared. And the only difference between this line and this one is that 2/3 times 3 is 2. So instead of minus 2/3 pi r times 3 dr dt, the 2 3's, 3 over 3 is 1. We just get minus 2 pi r dr dt. So this is the simplest expression we have for dh dt. But just as we feared, we have to figure out when h is 3 meters deep, what's r? What's dr dt? So we have to figure out a way to relate r to something else, something we know. And the only candidate is h, because if you think about it, we have already used the equation for volume. Volume is a function of the height and the radius. That equation isn't going to give us any more information. We have to figure out, is there another relationship between r and h? So we consider the diagram again. And one thing that you always notice in the diagram of a cone is that the height and the edge of the cone and the radius, they make a right triangle. So I kind of chopped out that right triangle out of the diagram, so maybe you could see more clearly. You have a right triangle, a very large right triangle, and a little tiny blue right triangle. And these triangles are similar. If you recall, similarity is when two triangles are similar when all their angles are respectively congruent. So look, we have two right angles, because the height of a cone is always perpendicular to a radius in the base. Two right angles. This blue angle is shared. And then if you remember the 180 rule about triangles, if two pairs of angles are congruent, I guess I can mark them congruent here. This one is also a right triangle, and this one is shared. Well, then this third angle is going to be congruent also, because of the 180 rule. Well, if they're similar triangles, and all the respective angles are congruent, then the respective sides will be proportional. So the radius divided by the height is always going to be the same. So the radius of the empty container, 2 meters, divided by its height, 4 meters, that's 2 over 4 or a half, is going to be the radius divided by the height at any point in time. So r over h equals a half, or r equals half of h. r equals 0.5h. That's always going to be true. And that's because these triangles are similar. We can also take the derivative of this little equation, and that tells us that dr dt is 1/2 dh dt. Well, now we can make a substitution. We can get rid of the r and the dr dt in our equation. This equation. And then we can simply solve for dh dt. Notice I'm not going back and using the equation I ended up with here. I'm going back to an earlier point where the substitution looks easier to make. You can do it any way that seems reasonable to you, as long as it's correct. So this is what we had, 2 cubic meters per minute is 1/3 pi r squared dh dt plus 2/3 pi r h dr dt. But now we know how to substitute r for h. So r is 1/2 h. So instead of r squared, half of h is squared. And dr dt is 1/2 dh dt. So I noticed that we have dh dt in both these terms, so I factored it out. And we have 1/3 pi times 0.5h squared plus 2/3 pi times 0.5h times 0.5h, or 0.5h squared also. And we have h equals 3, right? And half of h is 1.5. So 2 is dh dt times, this became pi over 3, times this is half of h, half of 3, 1.5 squared, plus 2 pi over 3, 1.5 squared. You're going to want to go over this a few times. Maybe write it down yourself, make sure it matches the video, to make sure you understand the algebra and the arithmetic. But notice pi over 3 plus 2 pi over 3, 2/3 pi plus 1/3 pi is just pi. So this is pi times 1.5 squared. That's how I simplified this. And pi times 1.5 squared then is going to turn out it's the coefficient of dh dt, so we divide by it on both sides. We get 2 divided by 1.5 squared times pi, or 0.28 meters per minute, is dh dt. That is a more typical complex related rate problem. It's worth studying and looking at over and over. I suggest you do it on your own and then watch the video again to see if you got the correct answer. Good luck.